Hello everyone. So this is the second part of my video lecture on detailed modeling of modular multi-level converter. So let's start. So in the previous video we have developed this detailed modeling of modular multi-level converter, and we tied it with a grid, and the grid is basically a three-phase source. So in the detailed modeling we have modeled each submodule, using the discrete switches and capacitors, and we are not using any built-in model or the aggregate model you call. So this model is ready, and now we are going to basically develop its control. Now in closed loop control, we have to we have to use the system parameters, and using those system parameters we have to control our inverter in such a way that it ties with the grid, and and more important, we have to control these capacitors so that they charge and discharge, and they work in a way that the voltage or the active and the reactive power are controlled. So let's get started. So first of all, we have to use the grid voltage. So here the grid voltage is this. So we are taking this go to block from here, right? And we also need the line current, and the line current is basically this IABC. So we have taking these two things, the grid voltage and the line current. Okay, next, since they are three-phase sinusoidal voltages and currents, so we need to convert them. Now we have different methods of converting these sinusoidal voltages into direct and quadrature voltages. Like we have ABC to DQ transformation, or we have ABC to alpha beta and then alpha beta to DQ. So ABC to DQ is a very common approach and more appropriate approach than transforming your sinusoidal signals to alpha beta and then alpha beta to DQ. So this is used widely. So we'll use ABC to DQ, ABC to DQ transformation, which is this one right here. So we'll connect this with this. We can copy this for the current as well, since in order to control the active and reactive power, you basically need to control the voltages and currents. Yeah. Next, we will take the repeating sequence and place it here. All right. Now in repeating sequence, we have to set its parameter, like will be the time values for this will be 0 to 0.02, which is 1 over 50, and we are interested to output like 0 to 2 pi. So pi is basically the constant. All right. Now we can simply wire this repeating sequence with this omega t. Okay, this is done. Now here we'll get three components: the direct component of the voltage, the quadrature component of the voltage, and the zero component of the voltage. Similarly, here we will get the direct component of the current, the quadrature component of the current, and the zero component of the current. So we can extract using the demux. So we can use demux and we can place it here. Now we have to use, since there are three outputs, so we can make it as 3. You can also resize it and simply you can connect it like this. You can copy this and place it here. Okay, let's move a little bit down. All right. Next, we can create some signals like using go to block, and we can name it as, this is our VD. We can make it as global, so we'll connect it here. This is the direct component of the voltage. We can copy it and connect it here. So this will be the quadrature component of the voltage. Similarly, this will be the zero component of the voltage. So for now, we are not using it, so we can just use this terminator block, and we can connect this. So this will not give the error when you are running the model. So sometimes it gives error and tells you that some outputs are not wired. So you can place the terminator to avoid that runtime error. Okay. Okay. Next, let's wire this as well. So we can copy this simply and connect it here. So this will be the direct component of the current. So we name it as ID, and I can copy this and I can name it as IQ. So this will be the quadrature component of the current. And similarly, I can just connect terminator right here, since I am not using the zero component. All right. Okay. Next, now we need we need some references for the active and reactive power. So let's say we can just create a go to block, not go to, but okay. So now here we need an active power reference and reactive power reference. So for active power reference, let's say we are creating a constant. So for now, let's say we say that we are interested in 100 kilowatts, let's say. So we create a go to, right, and we can just connect it here and name it as pref. So this will be our active power reference, right? Active power reference. Similarly, we can create a copy of this and place it here, and just let's say we randomly set this value, press OK. So this will be our QREF, reactive power reference. All right. Now we can take the from block right here. So this will be our active power reference. And then next we will have the reactive power reference. All right. Now here we'll use this direct component of the voltage right here. And okay, next what we'll do, we will use a divide function. We'll connect it here. We need a gain. All right, in this gain we need to set as 1.5, or we can say 3 by 2. We can connect it right here. All right, then similarly we can do with this as well. We can copy it, we can copy this and place it here. Right, we can connect this. Oh, it's not connected. We can connect this reactive power reference right here. We can copy this and place it here. It's not connected. All right, and we have to make it as negative minus 3 by 2. All right, next we need to use an add block like this and place it here. Similarly we need to place it here as well. Okay, next we will wire this here and turn the second sign as minus. All right, now we'll use the, let me connect it here as well and change the sign as minus. Now we'll use these current direct and quadrature component. So this is the direct component, will connect here, and this is the quadrature component, we are connecting it here. All right, now we need a gain again. Now in this gain, what basically we have to use, uh, the line, the inductor value that we have placed it here, which is basically 3 millihenry. So we need to use this. We can copy this and here we have to paste it here, and we need to multiply it with the omega, and omega is basically 2 pi f. So 2 multiply pi multiply f, where f is the frequency. So this is basically the omega L, and omega is 2 pi f. All right, now we'll connect this with the direct component and the quadrature component as well. So this is here, and this we can copy it and connect it here. So direct and quadrature component. Next, we are going to use the PID controller to control this. So we are using the PID controller. Now in this PID controller, we can set the values of P and Q. So the proportional gain, our proportional gain would be, for now it would be 8, and we can set the integral part of this as 3, right? Okay, that's fine. Yes, this is done. We can set it at PI since we are not interested with the D, so PI is okay. And yeah, now you can press OK. Okay, all right. Now you can simply copy it and use it for below as well. So we can connect it here and copy it and also connect it right here. Okay, after that we are going to use the sum of elements, not the sum of elements, but the sum, this one. We can also add one more plus. Okay, next we are going to use the sum, this one. We can add one more sign, plus, apply, and press OK. All right, you can increase the size of this block since it's a bit smaller, so you just drag this one. All right, now the size it's increased. Connect here, copy it, and do the similar thing right here. All right, next we are going to use the quadrature component of the voltage and connect it right here, the upper part of this sum block. And for the third, we are basically connecting right here. Similarly, we'll connect this one here, right? And on the lower part, we are going to connect the quadrature component of the voltage, this one. Okay, so they are connected and done. All right, next we are going to use the mux, so we can copy this. All right, now we can connect this here, and the second input would be this, and for the third input we can copy a constant and place at 0, and connect it here. All right, so next we are going to use the divide block, this one. We can copy this. Now whatever we are getting here, we need to divide it with the uh, with the half of the DC voltage. Since our DC voltage was 8,000, so we can place it like 4,000 here. All right. Now, next we are going to use the DQ to ABC block. So DQ to ABC. So the control part is done. So now we'll create the reference signal that we are going to use to generate basically the reference that will be used in the modulation method to generate the signals for switching. All right, so we can connect it here, right? Now similarly in omega t we can copy this repeating sequence and connect it here. All right, now next we are going to use the demux. So we can write demux here, and we can set the number of outputs as 3. Since this is a three-phase system, so we should have a 3 different reference waveforms. All right, this is done. Now we need to limit the reference. For that we can use the saturation block, this one. Now in the saturation block we need to set the limit. So the upper limit should be 1 and the lower limit should be -1. So plus minus would be our saturation limit for the reference signals. So we can copy it and connect with each of these. Now the output of this will be our reference signals. So this would be A ref, this would be B ref, and this would be C ref. So they are basically the reference signals. This is B ref and this is C ref. All right. So the reference signals are generated. So normally when you create a closed loop system, so you have to control the active power, the reactive power, and obviously the voltages of the converter as well. So the reference signal generation part is done. Next, what we are going to do is to use these references and a modulation waveform that would be basically a triangular waveform to create the modulating signals. And then the major part would be to develop a voltage balancing scheme for this grid tied detailed model of modular multi-level converter. So it will be done in the next part.